Hi, good afternoon, everyone. I welcome you to Fall 2025 Mining Series Seminar at Colorado School of Mines. My name is Matilda Ajuakujo, and thank you all for coming for today's seminar. And it's honored to introduce the speaker for today, and he's in the person of Dr. Lee, who is an associate professor and director for Kroll Institute for Extractive Metallurgy at Mining Engineering at Colorado School of Mines. He is also a member of the Critical Mineral Innovation Hub and also Center for Resource Recovery and Recycling. He has 20 years experience in both academic and the industry. Without wasting much time, let's invite Dr. Lee, and he's going to talk to us about mine tailing reprocessing and repurpose with mineral processing and extractive metallurgy. So let's now invite Dr. Lee. Thank you.
Thanks for the introduction. We still have one more minute. The students get a pizza, sandwich back there. Well, I think I can wait a little bit. Now it's full quiet. Anybody hear me okay? Yeah. Microphone works fine? Okay. All right, good afternoon. Welcome to mining seminar. I'm in charge of this class, so I'm happy to talk about my work. So I put the title like that, but it's general, introductory speech and about a little bit of experience that I've done for the last 5 years. So first step, I'm a process metallurgist. Most of you are mining engineering, and some of you and also process engineer. So we are the culprit who produce so much mine tailings because we got the product from the mine, and then we do crush, grinding, and chemically treat it and make a concentrate and a final product and dump the remaining majority of the material that miners mine. So we feel a little guilty for making that much mine tailings. So why do we have that much mine tailing? Because we do mineral processing and extractive metallurgy. So the objective of processing is to separate minerals into two streams: the concentrate value stream, and then tailings. And to do that, we got to do comminution. So size reduction to liberate and separate, right? Great. So liberate and separate is the utmost goal for mineral processing, and the comminution. We have to crushing and grind to make a fine particle. And the separation is to produce the concentrate and the tailing. The tailing goes to the other way, concentrate goes to specific process options. And the products, the concentrate for refinement to make the final metals, and then tailing goes to management, what we call tailing storage facility, TSF, or whatever we name it. So that's an overall mineral processing extractive metallurgy. So in the picture, so we have a mine, we crush the rock and the liberations, and using flotation is a metallurgy, and then separation, purification, concentration happening here, and then further refined to make metals, and then we get the final product. So that's a very simple 30-second mineral processing. And the tailings. So Professor Priscilla Nelson teach the series of the tailings. So maybe some of you seen this photo. So this is a tailing continuum. So from the tailing slurry out of the mill, so in the mill, we mix the ground rock with water and run through flotation, leaching, and many unit process. So typically that process contains anywhere between 20% and up to 50–60% solid. That means 80% or 50% are water. So out of the tailing dam, this is discharging. As you can see, this is like a slurry that which is mixture of a solid and the liquid. So it's only 20%, 30% solid. So majorities are water. So if we discharge this into the tailing pond, we need more space and an area to store not only the solid, but also the water. So we wanted to decrease the water portion. So we make this kind of a paste. So it looks like a toothpaste. So it flow a little differently, but it still contains 50% to 25–30% water. So it's much better, but if we can squeeze out more water, we can make this what we call dry stack or dry tailing. But dry stack is not, bone dry. There's still 15%, around 15% moisture in the dry stack. So that's transition between old days and these days, new application. So other example, as you can see, this is actual tailing pond from the tube or pipe. You can see the slurry coming out and a huge amount of area of the tailing storage facility. Majorities are water. And if you can make this kind of a thickened paste, then we can decrease the size of the tailing storage facility. And then if we can squeeze more water out of this material, and this is actually filtered, dry stack tailing. So we can, we need a much less space to store the huge amount of tailing. So that's a change of the scheme industry wanting to go into dry stack tailings. And different tailings coming from different mining operation. So first one is iron ore tail. We produce 18 billion tons of iron per year globally. So there's quite a lot of iron tail. So iron ore tail is finely ground material, and it still contains 30%, 35% iron. So iron concentrate is about 60–65%, but the tailing still contain 35%. I wish we had a 35% copper tail so we can go for it, but iron tail is still very high. And then potential rare earth elements. So where is the largest rare earth mine? In China, right? Bayan Noble mine in the Inner Mongolia. So what is that Bayan Noble mine originally? Started as a mine. It's an iron ore mine. It was not a rare earth mine. It's an iron ore mine, but they found rare earth. So now it's known as the largest rare earth mine. So there's a potential that we can recover the rare earth from iron ore tailings. And then the second one, copper tails. So a lot of copper mines in the US and South America. So copper mine tails, it often contains sulfide. So what happens if there's a sulfide? The sulfide oxidized to sulfate, produce acid mine drainage. So that could be a huge environmental issue. And then leftover copper and then other critical materials can be recovered. Okay. And then other example is phosphogypsum, phosphate tailings. So to make a phosphate fertilizer, the phosphate mine rocks is treated by sulfuric acid, and it's going to produce phosphoric acid and make a phosphate fertilizer. And the byproduct is tailing is what we call phosphogypsum. it's abundant, useless. I mean, there's not much usage of a phosphate, phosphogypsum. So I never been into this operation in Florida, but they said it's over 100,000 of acres covered by this phosphogypsum. So there are some relatively higher concentration of rare earths such as neodymium, praseodymium. So quite a few research institute and a university that are working on that project. And then the infamous red mud. So red muds come from aluminum industry. So from the bauxite, we do Bayer process, so high temperature alkaline process. And then the residue is look like this. It's a red, very finely ground material. And sometimes it contains some value. So such as gallium and some other critical material. And yesterday, DOE announced the gallium project, where we can make a 15 kilogram. They're gonna provide up to like a $6 million of research project. But the concentration of gallium typically in a bauxite is in the order of tens ppm. So very low, but because gallium is one of the critical material for the defense application, the US government wanted to develop a new technology. So those are the few examples. And then how much tailings that we produced so far, and then how much we produce per year. So total is about 280 billion tons. I couldn't imagine how much is that. And every year we produce about 8 billion tons. Oops. And then about half of them come from copper mine and gold, followed by iron and coal. So gold mine and a copper mine produce almost 70% of mine tailings globally. And then this is the size of the tailing, 217 cubic kilometers. And I Googled the size of the mine's campus. That's about 500 acres, which is 2 square kilometers. So if you put all those mine tailing on the mine's campus, it's gonna be 100-kilometer height. So 100-kilometer height is what they call Karen's zone or whatever. It's between the inner space and an outer space. As if we build put the mine tailings on the campus, we can literally reach the space. So that's a huge amount of tailing. So there's an opportunity, right? Last week, we have a big symposium and a workshop about critical materials, and the main subject was waste to mines, waste to value. So in 280 billion tons, and if we can squeeze out some of those critical materials, and theoretically we can provide the not only domestic but global metal demand, right? But there's a reason why the materials ended up in the tail. So, but there's always an opportunity. So this is the amount that we need to deal with, and then we need to tackle. So what do we do with it? What do we do with the mine tailings? So current proper storage or safe storage. So we place it into a tailing storage facility. And then hopefully it's safe, but you've seen mine tailings failure. So it could be safe in a certain time. So the failure of the tailing dams probably matter of, when, it's not if. So that's the current, state of the art, proper storage and a safe storage and monitoring the geotechnical aspect. And then we can utilization or reuse. And then by doing that, we can do, mine tailing valorization. We try to reuse it and create more value. And then also we can recover critical materials and then make some valuable product out of mine tailing. So that's we know what to do, and I mean, a lot of people study and investigate. So this is the one photograph that after the tailing dams failure in Brazil, Brumadinho in 2019. So 272 people lost their life, and the economic impact is $1 billion. And I think the Vale, BHP, their executive, they went to prison and fines, the amount of fines in the order of $1 billion. So that happened in January 2019. So BHP announced what they call BHP Tailings Challenge. So this is the purpose of this global tailings challenge is to promote the development of innovative solution for repurposing copper tailing. And they help with the Chile Foundation through, expand. And it's a global competition to find out the solution and then transform that idea to innovate the business model. So it was 2020. And the BHP Tailings Challenge launched in June. So there was an open call, studied a proof of concept and a pilot and on-site industrial pilot scale facility. So you can guess how many people applied at the open call. So there was 153 applications from 19 countries. So they picked 10 out of the 153, and they provide a small amount of money, just a drop in the bucket for BHP, but 10 group. And then they're supposed to pick 3 teams to go for pilot scale, so with a $300,000, but they were able to pick only 2, and then that was April 2022. And then final decision or final winner was supposed to be announced in end of 2022, but guess what? What happened in April 2022, right? COVID. So everything's halted. So there were 2 teams. The one team tried to make fertilizer out of mine tailing, and the second team tried to make some, recover copper and then make some other material. And then only one team is currently working with a BHP still, but they never award the $8.6 million award. So I don't know what happened, but it is what it is. So, the BHP Tailing Challenge is, when I was in Arizona, we found the startup company. So it's called Jaeheon Technology. So the goal is to extract more metals and then produce the byproduct out of mine tailing. So the process is modular, so we can do, quick treat in one side, and then we can move to the other side relatively, quickly by using the, fast, quick deployment. And it's very highly replicable. It's not only work for the copper tail, but also work in the gold tail and other mine tailings. And it's zero waste. And it's a daunting task, but our ultimate goal is to treat the 100% fresh tail coming from the mill and the copper operation that they produce usually like a 200,000 ton per day. And then also the carbon negative. I guess we're not supposed to talk about that in this administration, but we can also do that. So input feed. So we received the Antamina copper mine in Peru, one of the largest one. So we ran through chemical mineralogical analysis. So ChemScan showed greater than 6% pyrite in the feed, because through the mill in the copper operation, they wanted to reject the pyrite. And XRD shows it has about a 4% calcite and a quartz, and ICP shows a metal concentration, arsenic, copper, zinc. and a particle size is 50%, I mean, smaller than 100 micron. So it's a typical copper mill tailings. And then this is a chemical analysis of the tailing material. So average copper grade going into the mill these days, probably less than 1%. And I'm pretty sure Antamina's operations, their mill feed grade is around that. So after all those processing, they throw away the tailings. And this is the concentration of copper. So 0.07, 0.06, 0.07. We had 3 different samples. So the copper grade is less than 0.1%. So there, if they treat, let's say 1%, their copper recovery is pretty damn good, over, I mean, 90%. And then in the tail, what do we have? We have a sulfide. So sulfide sulfur is a 2%. And then small amount of arsenic in the ppm level. And there's a cobalt in the ppm level, and a nickel as well. And then also neodymium, I better not highlighted this, but neodymium is here, praseodymium is there. So it's an 18%, 4%. It's there, but I mean, I don't think it's economic enough to recover. But by the multi-element ICP scan, it's going to provide what's in the tailing material. So our focus is, because BHP wanted to process their copper mine, so we tried to recover as much as copper or the co-products such as cobalt or nickel. So what we did was what we call desulfurization. It's a simple sulfide pyrite flotation. So multi-stage pyrite flotation to get a clean pyrite concentrate. And during that, copper, cobalt, nickel, arsenic even, and a zinc that associated with a sulfide is going to come to the concentrate. So we make the concentrate, and the sulfide content is over 50%, and we can upgrade those base metal. And then this is the recovery of those metal. So by doing that, we can create clean tails. So copper mine tails, first tails, contain extremely small amount of metals, but also high concentration of sulfide and some other metal. But after the mineral processing, we create a second tail of tail. So that tails contains low enough of sulfide and then other much less concentration of toxic elements. So we can make those to produce the other materials. So why we are doing that is we will talk about that, but yeah. So we made a clean tails and then use that for making some other, the value-added product. So this is the flotation result after the mineral processing from the feed material. So this is the feed, and then this is concentrate, and that's an upgrading factor. So 0.07, 0.06% copper becomes 0.8, 0.4, 0.3. So the average is about, almost 9 times upgrading the copper concentrate. So it's a waste. It's not economic, but 0.8%, if we have a 0.8% copper resources, I think we can process and, get a good profit out of it. And then, as you can see, I mentioned arsenic. Arsenic comes to the concentrate. So it is concentrated on sulfide and pyrite, and the moly, zinc, and selenium, other thing. As you can see, the cobalt is also concentrated in several hundred ppm level. So we increase the metal content, sulfide, sulfur, And then all the other thing is in the tail, including rare earths, because rare earths is mostly oxide. And we made a benign tail. So use that benign tail to make some other product. So this is overall flow. Oops, sorry. This is overall flow. So in a concentrator, waste material tailings coming into a tailing storage facility. And then by the desulfurization, we can have a concentrate. And then the concentrate goes to bio-oxidation or bio-leaching using specific microorganism to oxidize the sulfide sulfur to sulfate and then produce the sulfuric acid. And then also oxidize the ferrocyan that come from pyrite and another iron source. We can oxidize to ferric iron, and then ferric sulfate in a sulfuric acid solution will be formed. So we can create those two key lixiviant for copper operation. So in mostly large copper mine has the heap leaching, dump leaching operation. So they can use sulfuric acid and ferric sulfate. And then we can make the geoform using the tails of the tails, which is cleaner because we get rid of the sulfide, pyrite, and then also some other the toxic sulfide associated elements such as arsenic, cadmium, nickel, cobalt, zinc, and all the other the metals. So application of this whole process is to, reutilize the tailings and then supply the key lixiviant and then make the new construction materials that can be used for backfill and the support materials and insulating material. So next step is, this is one of the example. As you can see, looks like a sponge. So that's why we name it a geoform, and using cleaner tails from the flotation, followed by the bio-oxidation. And a lot of mine tailings materials were used to produce construction materials, and mainly using geopolymerization. So geopolymerization, you add caustics and a high temperature curing, and then we can make a good, strong concrete alternative. But the issue of that procedure is there are still lots of heavy metals, and also the high amount of caustic that eventually work like a leaching agent. So when it is exposed to water, it's going to mobilize the heavy metals. But a geoform, you use much less caustic, only enough to activate the materials, and natural foaming agent to use, and no high temperature curing, and then better immobilization of heavy metal. So when we go through the different tests, the heavy metal isn't going to release to environment. And then one other advantage is can be used by 3D printing or shotcrete, so that material can be applied in a different way, and then it can be used as a sand alternative and a different additive, and then also cement clinker. So cement clinker is, it's difficult one, because cement industry, the margin is so small, so they don't want to, change their flow sheets, but it could be a good candidate for cement alternative to cement clinker. And then as a cement alternative, if we can change the recipe of this product, as you can see, this looks like a solid material compared to previous slide. This one is more like a sponge. So change the recipe, we can make a different form and a different physical characteristics, and we can make the different material for different application. And geoform, the reason why we made a geoform is to use in one of the mine is currently developing in Arizona, the Resolution Copper. So it's an underground mine that's going down about a mile deep. So if you go Leadville is 2 mile high. It's much cooler in summer. So guess if you go down 1 mile, it's pretty, balmy, right? So we tried to develop a insulating material in an underground mine. So this one was developed. So thermal conductivity is pretty low. So typical concrete is about 1.6 to 3.2 watt per meter Kelvin, but a geoform is only 0.1 watt per meter Kelvin. And as we can guess, the density is pretty low. It's really light. So concrete, the gangue mineral, all those things, 2.4, 2.3 gram per cubic centimeter, but this one is only 0.32. And the settling speed is very fast. It could be molded like this, and it could be sprayed. And one of my students, is still working on, making this. We can put it in a mold and easily make a different shape and a form. So instead of, other than tailings, other than geoforms from the tailings, we can recover copper. So the amount of copper tailings that we can reproduce, then we can reserve, we can get about 20% of the requirement. So 20% is, global copper productions, about 22 million tons. So we can produce additional 20% out of it. And the nickels, we can produce about 10%. And the cobalt is a little lower, it's only, 3.5% additional metal production by reprocessing. And then the other one is multi-crystalline silicon. So in the tailings, most of them are aluminosilicate. So for the solar panel, we need a high purity silica. So we talked to Vale, BHP, and Rio Tinto many times. They wanted to make a high value product from the tailings. And one of them is always high purity silica. So they know they can sell the multi-crystalline high purity silica to the solar panel manufacturer. But it's not easy because silica and aluminosilicate always associated a small amount of impurity. So a lot of people try to make that. As you can see, in 2027, it could be almost like a $10 billion industry. So people try to make the silica out of it. And I already mentioned most of them. The geoform is the supporting material in a different application. So we can also use the sand and a fill additive and a soil addition and also micronutrients. So, I mentioned that somebody tried to make a nutrient or fertilizer out of a mine tailing. So there are some nutrients that we can use. And sulfuric acid is used for the copper leaching, but also fertilizer and then also chemical industry and many other applications. So if you can make even high purity sulfuric acid, it's we call the semiconductor grade sulfuric acid. We can sell much, higher price. And ferric sulfate is commonly used oxidant in the mining industry. So it can be used, but also wastewater treatment and textile industry. So there are many other applications. So these are other, potential product out of this, copper tailings. And then I also mentioned about the environmental side. So we want to make a brick, but it has to be environmentally, friendly. We don't want to build our house using toxic brick. What if the brick release toxin when it's rained? So we don't want that. So we made a product and went through the test. The TCLP is a toxicity characteristic leaching protocol, and SPLP is synthetic precipitation leaching protocol. So this EPA standard procedures to measure the how much heavy metal comes when it was exposed to water in another environment. So as you can see, this is the lab toxicity level of the tailings, and this is the drinking water regulation by the EPA, and this is the geoform that we fabricated. So this is much less than even drinking water standard. So that's one of the bigger advantage, because we made a tailings of the tailings to get rid of heavy metals. And one other important thing is the CO2 sequestration. So there was a calcite naturally in the tailings, but during that forming process, we found out increase the concentration of calcite. So Joe over there, he's gonna do a series of experiments. So to find the best recipe to get produce more calcium carbonate to sequester the CO2. So that's we work with the National Renewable Energy Lab, and then we use the XRD to find out the calcium carbonate content, but they have a better, more advanced technology to analyze the calcium carbonate content from the brick. And some other, advantages, SCM cement, supplementary cementitious material. So instead of just a natural, cement industry, we can make the substitution for the cement, and then make a strong structural materials, and then we can also do CO2 offset by using this process. So the overall industry benefit is from the concentrator, we make a metal concentrate, and in this case, copper concentrate, and concentrate goes to typically smelter, and the tailing goes to tailing storage facility. And the tailing storage, the operating and the maintenance cost of a tailing storage facility is not cheap. So if we can get rid of this tailing storage facility, then global mining company can reduce the operating cost significantly. So these are, I don't want to read every line, but you can see the benefits. So we can increase the metal recovery, and then we can have a lot of different benefits out of the reprocessing those copper mine tail. And then we ran through lab scale, benchtop scale, and this is the lab pilot test that we built in Tucson. So as we can see, mixing tank tailing comes here. This is surge tank kind of thing. And then we have a rougher flotation, and then we have a cleaner flotation and a small, tiny scavenger circuit as well. So we, multi-step flotation. So we concentrated those sulfide and pyrite, and the sulfide concentrate goes to another surge tank right there. And then that's going to feed material to this, thermal blanket wrap, the bioreactor. So you maintain around 35 degrees Celsius to make those microorganisms happy, so they can oxidize the sulfide and oxidize the ferrocyan. And then the solution coming in, because after the bioleaching, all those metal will be dissolved in the solution, and then we can use conventional solvent extraction, ion exchange to recover metal, but we can also precipitate it as a sulfide, so multi-metal sulfide, and then we can send it to the smelter operations. And the little tiny 3D printer is also there, so we demonstrated the capability of a 3D printing. So different factors. So the critical materials is one thing. Copper is one of the critical materials, and then we can also recover cobalt, nickels, and many others. And also there's a shortage of a cement product, so we can supply into the cement industry. And then this is an advantage for the industry. So the legacy cost of maintaining tailing storage facility can get rid of by this overall activity. And a few advantages: environmental advantage, societal advantage, and then also the capital can be funded by the ESG standard. So I think I already mentioned those products. We can produce all those different product from the tailing waste material. And we also did one case study. So because it's an antimina in Peru, and then also currently we are working on escondida material in Chile. So if we build 10 million tons per year mine tailing reprocessing plant in South America. The capital cost is about $165 million, and operating cost is about 1/10 of the capital cost. And we have a 36% rate of return, and then we can get the CO2 credit throughout the process. So it was quite, attractive process. And strategic partners. So BHP is, they started the BHP Tailings Challenge. So they provide all those data and financial support. And then Metso is the to help us to license the geoform and also equipment fabrication. And then Clariant is chemical company to develop green chemicals for flotations and flocculants and other reagent. And Stantec is working on engineering side. So we are collaborating together. Decarbonization strategy. Waste reduction. The ultimate goal is waste reduction of 100% when the fresh tailings come, and then we wanted to treat 100% and tailing as a cement additive, and then geoform capable of carbon captures made of 100% tailing. Another advantage, it's really, not an expensive process. We don't use like a expensive the plant that cause high capital cost. So it's really low cost. And then also it's much less than the tailing storage facility maintenance and operating cost. And as I said, it's wanted to get rid of 100% and then net zero. And then we can make a new construction material. So it's a, byproduct. So the mining company can sell. Without those economic advantage, I don't think the global mining company is going to invest. So they don't want to lose money because most of them are public company. So if they want to do some project and they lose $100 million per every year, and then it's not going to be approved. So they're going to be, economic benefit. So the last conclusion is the process that we developed and then I worked for last 5 years, and we can recover metals and then also produce the sulfuric acid and ferric sulfate, which is key thing from bio-leaching and a bio-oxidation. We don't need to provide chemicals, and then the byproducts, so we can have many application. And then CO2 sequestration. And then also we work with the other company, and then we tested it in the gold and the silver mine tails, and then lead zinc tailings, and then phosphogypsum and then manganese tailing. Different process, but it eventually, ultimately is very similar. We want to make it cleaner tails and then make the cleaner or environmentally, friendly byproduct. So the company can sell and recoup the capital and operating costs. So that's all I have, and thank you very much for your attention. And I can answer if you have any questions. Question.
Thank you for the presentation. That was actually very informative. One question I would have is there a possibility of using this with similar technologies on historical tailings as opposed to fresh tailings?
Yeah. So now we are working on two things. So one is fresh tailing that BHP just delivered from Escondida. And then also in the Globe Miami area, there are a couple of BHP legacy sites. So we work with the BHP legacy tailings team. They have an office in Tucson, so we work on legacy tails and fresh tails. Hassan?
Talking about the economics of the group, you're saying the shareholders are not interested in the whole business of recycling the waste, but it's government that are actually interested in this kind of waste. So in this case, we're going to South America, and the government, like in America, trying to rework this waste in markets. how is the collaboration going to be like offsetting geopolitics and progress?
Yeah, I mean, I have worked on that processing side mainly, but other people, I mean, did a market study and collaboration with, I mean, local government and also the national, I mean, central government. So, I mean, byproduct, the cement product and construction material is not really, really high value material. So the margin is so small. So not only the construction material for building material, but also majority can be used on mine site to build like a whole road for the open pit or, I mean, the other infrastructures in the mine site. So, I mean, like you mentioned that it's closely work with the government, local government, or, I mean, whole country or whoever had an authority. So that's I mean, very important. So it's all collaborative effort. Kadri? Yeah.
Yeah, I have been involved with two plants and tests in US and South Africa. You could not get the biological work.
In copper or gold or? Gold, okay.
And so I have technical suspicion in getting this biological work. And also, if you go to slide 22, wonderful. I have not seen any refractory or processing that will cost $60 a ton. And for 10 million tons per year, I mean, that to get you costs.
I mean, flotation is really cheap, right? And then bioleaching, we started, I mean, we inoculate the microorganism and then they're gonna do the work. So, I mean, this is in South America, not in the US. So I know it's I mean, much lower than the typical number that we have, but I mean, this is the one that we studied. So that's what, I mean, we have. Okay, okay. And then bioleaching, I mean, copper industry, I mean, successfully used and currently using bioleaching of sulfide material, particularly in the secondary side, but the primary side, I mean, we try to break through the chalcopyrite and other primary sulfide bioleaching, but I mean, when I work for company, I mean, I successfully demonstrated the bioleaching of a primary, I mean, sulfide, and then even company built like 1 million tons of a demonstration plant on site, so it was, I mean, successful.
Yeah, you did.
Yeah.
There is not a single bioleach capacity plant operating. That's the chemistry. You know, I've been doing it for many years, and we don't have it.
No, I mean, that's not true. I mean, we use currently Freeport use the bioleaching. They operate the bio heap in Morenci and then Cerro Verde and then El Abra in Chile. Yeah, it's a plant level. Yeah, just I mean, full industrial scale. In Cerro Verde, like their bio leach pad is, I mean, literally like a half mile. So they are running, and then in the gold industry, there's no gold bio-oxidation plant in North America, but Australia and in Africa, they are doing concentrate bio-oxidation of pyrite column. And then it's, I mean, they produce a lot of gold out of that processing option. Yeah, we can talk about that. And
yeah, great presentation. Really great. A couple of things, use case study about Florida for phosphate gypsum.
Yeah.
The problem with that is it's under current US regulations. It's radioactive.
uranium, thorium, right?
You cannot sell it in the open market.
Right, yeah.
Considered a waste.
Yeah,
Hazardous waste.
right.
So that's, I mean, the regulation.
Sure. Yeah. So we did it, yeah, go ahead.
No, a couple. I haven't seen an update, but marine disposal or tailings, I mean, it's widely done in South America and Southeast Asia and in places in Africa and Brazil, right? CSI stuff in the ocean.
Yeah.
That, none of that is included in the total tons that's being recorded, right?
Yeah, I guess the total ton is on the surface, yeah. I don't know how much tailings goes to the ocean from the Grasberg, right?
Oh, yeah.
Yeah.
But you know, like that showed on Arrow Group.
Yeah.
They're talking 100,000 tons a day.
Right, yeah.
Right, so.
Yeah. That's an environmental, I mean, more like an environmental issue, right? Cool. Any question? Oh,
On
yeah.
the chat, no, on the chat, I guess.
Oh, check. There are bio-leaching plant operating in Finland and Jaeheon for cobalt, yeah. So some of them, Professor Steve James mentioned, thank you, Professor James, so, yeah. What was the comment, first comment, Professor Miller? So,
Oh, no,
I mean, I want to say something, but I forgot.
you know, like, Florida, the reason they have.
Oh, yeah, right, yeah.
Talent.
Yeah, phosphogypsum, we work with a mosaic, I mean, not here, I'm personally as a research project, try to develop a project with a mosaic, so their rarest concentration is much higher than like a coal ash or, I mean, other thing, it's 100 ppm, and then some other, their product is even more, so we can, I mean, economically recoverable, but the issue is thorium and uranium, and also radium that produce a radon gas. So we study that, and then also talk to energy fuel. So if you make a concentrate, let's say neodymium praseodymium concentrate, who's going to process with a uranium thorium? Only place is the energy fuel in their mill in Utah. So we, well, I mean, talk to them for the potential, I mean, project. So, I mean, we try hard to get those kind of I mean, project for the phosphogypsum. Yeah, that's a good point. Yeah. Right.
The other thing, I just passed a PhD to global end, they're taking, what the form of the iron is. So remember when they went back through and were mining, all their old dumps and tails? Miracle Grow, the plant food, mine, some sort of ferrous iron from them for, you know, byproduct of, you know, production for plant food, right?
Okay.
And it was an interesting process, but to my knowledge, that's the only copper mine that's mining waste that's making money. Is it, you know, any others in North America?
No, I don't think there's anybody who make money out of the tailings yet. So yeah, it's just maybe one of those. It is, yeah.
Yeah, regarding the mine from tailings, I know a mine in Turkey, they try to store the tailings in the sea.
Oh, okay.
Black Sea. So they have, I think they have sphalerite and catastrophic. So they get the copper as an ore and they put the zinc in the sea.
Okay.
I think it's 50 meters below in the sea.
Okay.
You can store it in case of price of zinc increase or something. You're gonna extract.
Oh, they're gonna extract from the ocean again. Okay. That's what I mean. Professor Miller mentioned, like a ocean disposal, like a Grasberg mine and some other. I mean, they dump, like particularly in Indonesia, they dump pyrite concentrate. There is a few ppm gold in there. So if you're interested, you can go to Grasberg mine and get the gold out of it. If not, thank you very much again.